Welcome back, everyone. Today I'm going to do some more examples of proof by cases. And as I do, I'll mix in some of the other proof methods as well. So this is a good set of exercises for you to practice on. Okay, so here's an example. And I want you to think for a minute about how you would approach this question. And I hope the words that eventually sort of circulated their way into your brain were contrapositive. And what makes you think contrapositive about this? The thing that you should note that might make you think that the contrapositive is a good idea is this endless supply of nots in the statement. It is not a super nice hypothesis to work with when you say something does not divide something else. But when you have something that does divide something, that gives you something much more concrete to work with and lets us avoid, hopefully, thinking about the division algorithm. So, as a proof here, we're going to prove the contrapositive, which says, if 3 divides x or y, then 3 divides x times y. And so, while you might not have been inclined to think cases from the original version of the question, now that we've written down the contrapositive, we have this or here, and that or, in my hypothesis, now makes me think that I'm supposed to use cases. So, case 1, 3 divides x. So, that means there exists k, such that x equals 3k. So, xy is 3ky, and so if m is k times y, then x times y is 3m, and so x times y is a multiple of 3. And then I'll write down almost exactly the same thing for case 2. And so that covers both the possibilities. 3 divides x, 3 divides y. Now, the astute among you might notice that this proof of this case and this proof of this case are almost identical. And so, in a sense, maybe we sort of wasted our time writing down both of these. And there's a fancy mathematical phrase that we can invoke in order to avoid writing down both of these. And so the magic phrase is without loss of generality. So when we go ahead and write this proof, I'm going to start with a sentence like, suppose that x and y are integers, and without loss of generality, that 3 divides x. And when you see this written out by hand, you will almost always see it written as WOLOG, just the abbreviation for without loss of generality. But once I do this, then I get to just go ahead and say, well, then there exists k and z, such that x is 3 times k, and so x times y is 3 times k times y, and so if m is k times y, then x times y is 3m, and so x times y is a multiple of 3. What did we really do here? Well, it might look at first like we just missed a case. But what without loss of generality here is letting us do is to look at this statement that we want to prove, which is, if 3 divides x or y, then 3 divides x times y. And here, this statement is symmetric in x and y, and that's the key observation here. Okay, and what do I mean by symmetric in x and y? I mean that if you exchange x and y, it doesn't change anything. I'm saying the same thing about x and y in the hypothesis, namely that 3 divides x or 3 divides y. Those hypotheses are exactly the same. And then the conclusion is about x times y. But as we famously know, x times y is the same as y times x. So even if I exchange x and y, I get the same answer. And so what that means is, as long as you identify that the hypothesis here says the same thing about x and y, and that the thing we're talking about in the conclusion is unchanged by switching x and y, well, then we'll notice that this statement is symmetric in x and y. And so what does that mean? Well, that really means that if you could prove it in the case that 3 divided x, then you could just swap x and y in the proof, and then that would also be a proof in the case that 3 divided y. And that's exactly what without loss of generality does. That is exactly why when we wrote up the proof in both cases, they looked exactly the same. And so this is just an alternative way of writing that up that you'll see a lot. Now, I want to caution, without loss of generality has a very precise meaning. You cannot use it just because you're in a proof with cases. You can only use it if you really know that all the cases are the same. So I really want to stress here, without loss of generality doesn't mean, well, I see there's going to be a bunch of cases and I don't feel like doing them all. It really means I know from the statement of the problem that all of the cases are going to be exactly the same. Now, as a result, the use of without loss of generality as a value proposition is probably quite negative to you as someone who's beginning proofs. The reason for that being that if you use it, then if it works, you get to save writing a few things. But if you use it and it doesn't work, then your entire proof is wrong because you've basically only presented one case and you needed the other cases for it to be a complete proof. So you have to use great care with this, and I would say that most of the time you should view it as sort of an advanced technique that you're going to see a lot in textbooks when they're doing proofs, but you probably should not jump straight to using it unless you're very confident. Now, I'll note one time you can use it is if you've already written out all of the cases and you realize that, like in this case, both of the cases were the same, in which case then you might identify after you've done the work that, hey, this would have been an appropriate time to use without loss of generality. Next up, let's look at this question. We want to prove that for all real numbers, we have this inequality, that minus 5 is less than or equal to the absolute value of x plus 2 minus the absolute value of x minus 3. And that, in turn, is always less than or equal to 5. Now, proving inequalities will quite often involve cases, but one thing that means that proof by cases is almost certainly going to be involved is any time an absolute value shows up. The reason for this is that absolute value itself is defined by cases. Namely, the definition of absolute value of x is that it's x if x is greater than or equal to 0, and it's minus x if x is less than 0. And so really, if you think about what's happening with a piecewise function, really this is describing cases. And so as a result, when I go to look at this, and particularly when I go to evaluate the middle, I need to know something about x to know how these absolute values resolve. Namely, is the absolute value of x plus 2, or is it minus x minus 2? And, well, half the time it's one, half the time it's the other. I need to know some information about x to know for sure. So let's write down a proof. So we're going to suppose here that x is a real number. And I need to decide what my cases are going to be. If I was looking at a just regular absolute value, my cases would be whether x was bigger than or equal to 0 or less than 0. But in this problem, I'm actually looking at the absolute value of x plus 2 and the absolute value of x minus 3. So I really need to know if x plus 2 is greater than 0 or less than 0, and whether x minus 3 is greater than 0 or less than 0. So let's start with the case when x is less than minus 2. That will make the thing in this absolute value negative, and it will make the thing in this absolute value negative. Next lesson. When we're proving a statement about an inequality, you cannot start by writing down the inequality. This is a bad habit that you've probably picked up in calculus classes, where when you go to solve an equation, the first thing you do is write down the equation. If you're trying to prove an equality, or if you're trying to prove an inequality, and the first thing you do is you write down that inequality, well, there's nothing you can do to prove it, because you've already written it down. You've already asserted the thing is true. So our goal has to be to start with a thing that we know, and work towards this inequality. I'll show you what I mean by that. So we're supposing here that x is less than minus 2. So then we want to look at this absolute value of x plus 2 minus the absolute value of x minus 3. That is, I'm just looking here at the middle part of this inequality. And since x is less than minus 2, x plus 2 is negative, and so this is minus x minus 2. And since x is less than minus 2, x minus 3 is even more negative, so the absolute value of x minus 3 is minus x plus 3. And so if I do that out, then this works out to be minus x minus 2 plus x minus 3 is minus 5. So in fact, actually, if I take any x that's less than minus 2, and I plug it into this middle piece of my inequality, I always get minus 5, no matter what x was. And one fancy important property of minus 5 is that, in fact, minus 5 is always between minus 5 and 5. And so since this quantity is just a really complicated way to write minus 5, I get the conclusion that I want, which is that this absolute value business is between minus 5 and 5. And you might, by the way, ask yourself before I write down the next case, how many cases do you think there's going to be in this proof? And just so you'll know if you got the answer right, 3. There will be 3 cases in this proof. For my second case, I'm going to pick x is greater than 3. Why did I pick x is greater than 3? Well, if x is greater than 3, that's when I know both of these absolute values are taking an absolute value of something positive. Because if x is bigger than 3, x plus 2 is bigger than 0, and x minus 3 is bigger than 0. And in a very similar fashion to the last case we did, in this instance, when x is greater than 3, it turns out this quantity in the middle of our inequality we're trying to prove is identically 5. So, although it's not at all obvious, if you look at this weird absolute value mush in the middle, this thing, in fact, always gives you minus 5 for x less than minus 2, and it always gives you plus 5 for x bigger than 3. That's what we've just shown. So I said we're going to do 3 cases. I've done 2 cases. We actually kind of know now, if we think about it, what our third case has to be. Namely, our third case has to be every x we have not yet considered. Which x's have I not yet considered? Well, the x's I haven't yet considered are x's that are between minus 2 and 3. So our last case is that our x here is between minus 2 and 3, just like that. In this case, what happens to the absolute value of x plus 2 minus the absolute value of x minus 3? Well, because x is bigger than minus 2, this x plus 2 is positive. So when I take the absolute value of it, I just get x plus 2. Well, what about the absolute value of x minus 3 part? Well, since x is less than or equal to 3, x minus 3 is negative. And so when I go to take the absolute value, I will get the negative of x minus 3. And when I subtract a negative, I get a positive. And so at the end of the day, what do I get? When x is between minus 2 and 3, this weird absolute value mush is actually 2x minus 1. And now our worst fear has been realized. We actually have to prove something. Namely, I have to somehow prove that 2x minus 1 is between minus 5 and 5. And the way I'm going to do that is to use my hypothesis here, which, remember, as has come up a few times, what this hypothesis here really means is x is greater than or equal to minus 2, and x is less than or equal to 3. This stacked inequalities is really just shorthand for saying 2 inequalities. So since x is greater than or equal to minus 2, what does that tell me about 2x? Well, that tells me that 2x is greater than or equal to minus 4. And well, then what about if I subtract 1 from both sides? Well, then I will get 2x minus 1 is greater than or equal to minus 5. Well, that was a nice coincidence. Just doing the standard inequality manipulations happened to turn the hypothesis that x was greater than or equal to minus 2 into the fact that 2x minus 1 was greater than or equal to minus 5, which is the thing I wanted. I have to do the same thing with x is less than or equal to 3. And again, beautifully, it works out that we end up with 2x minus 1 is less than or equal to 5. And thus, in this case, we've shown what we wanted, which is that this absolute value mush is always between minus 5 and 5. And we've now handled all the cases, right? Every real number is either less than minus 2, greater than 3, or between minus 2 and 3, where this between is including minus 2 and 3. I'll note, by the way, you could also have included minus 2 and 3 in either of these cases, so you could have made this less than or equal to, it wouldn't have changed the proof at all. Or you might even be tempted to make 5 cases where you handle x equals minus 2 and x equals 3 separately. That also works, whichever of these things you want to do. Anyway, though, that finishes this proof. Here's another example. Let's prove that if x and y are integers, neither x nor y is a multiple of 3, then x plus y is a multiple of 3, or x minus y is a multiple of 3. I'll give you a minute to look at this, and think to yourself, what proof method would you like to use? And probably what you think of when you look at this is contrapositive. Because there are a lot of things about this statement that scream contrapositive. Let me line them out for you. There's an or in the conclusion. We really like contrapositive for ors in the conclusion. We have a hypothesis that's about something that things aren't. Namely, we'd much rather know things are multiples of 3 than know that they're not multiples of 3. And so for these and more reasons, likely the first thing you try when you do this is to write out the contrapositive. However, this is not a proof by contrapositive. How do you know that? Well, probably you try and prove this by contrapositive and don't succeed. And so, we ultimately are going to have to, for this proof, fall back on direct proof. So we're going to need to make the hypothesis here, suppose x and y are integers, and neither x nor y is a multiple of 3. Now, fortunately, because of the division algorithm, I'm not completely stuck with the hypothesis that x is not a multiple of 3 and y is not a multiple of 3. Right? Because remember, all integers fall into these buckets, the 3k bucket, the 3k plus 1 bucket, or the 3k plus 2 bucket. And the 3k bucket is the multiples of 3. So what we're really here saying is that x and y are both in the 3k plus 1 or 3k plus 2 buckets. So by the division algorithm, we can go ahead and write x is 3k plus a, y is 3l plus b, where these a and b are the remainders, where remember they're supposed to be between 0 and 3. But because x and y aren't multiples of 3, they're not 0. And in the statement of the division algorithm, they have to be strictly less than 3, so really that means a and b are just 1 or 2. So how many cases does that give me? If you said 4, you're correct. There are going to be 4 cases, based on what a and b are. So my first case, what if a and b are both 1? Well, then I claim that if you take x minus y, you get 3k plus 1 minus 3l plus 1, which is going to be 3k minus 3l, which is going to be 3 times k minus l. And so if m is k minus l, then x minus y is 3m, and so x minus y is a multiple of 3. Now, please remember, my conclusion here is x plus y is a multiple of 3, or x minus y is a multiple of 3. So just showing x minus y is a multiple of 3, that's plenty. That handles this case. Now, you might pause and ask, wait, how did he know it was going to be x minus y and not x plus y? Well, I can kind of imagine what would happen if I took 3k plus 1 and added it to 3l plus 1. That would give me 3k plus 3l plus 2, which would be in the 3k plus 2 bucket, not the 3k bucket, so that's not the one I want. I'll handle the a equals 2, b equals 2 case next, because this case is almost identical to the previous case. It's not quite at without loss of generality level of identical, but I get the idea. I subtracted 1 from 1 in case 1, I'm going to subtract 2 from 2 in case 2. When a is 1 and b is 2, I actually want to add x and y instead. And so the magic of what happens here is that in fact 1 plus 2 is 3. And last but not least, we can do case 4, which is that a is 2 and b is 1. And so just like the other cases, case 4 kind of writes itself once you figure out what's going on. And so we have finished the proof. Now, I've given this exact question as a test question many, many times, and this is the solution that almost everyone gives. But I often have students ask afterwards, do you really need to use 4 cases? Isn't there some way around it? It seems like these cases are so similar, I should be able to sort of squeeze some out of it. And the answer is that if you think very carefully about this, which is probably not the appropriate thing to be doing during a test if this were a test question, but if you set that aside and you think about it carefully, you actually can write this down in 2 cases. And namely, those 2 cases, if you want to do it, are the cases where a equals b and where a is not equal to b. If a and b are equal, then your proof is going to look like case 1 and case 2. In fact, we even kind of remarked upon that at the time, because then really what would you have? You'd have 3k plus a minus 3l plus a, the a's would cancel, and you would get 3 times k minus 3 times l, which would then work out exactly the same way. So that would handle the a equals b case. The other case, the second one, is that a and b aren't equal, in which case when you add x plus y, you're going to get 3k plus a plus 3k plus b, which is 3k plus 3l plus a plus b. And the only thing I know about a and b is that they're not equal, so this maybe seems worrying, but if you look back, a and b both came from the set 1, 2, so even though I don't know what a and b are, if I have written this proof in this 2-case method where I'm having my second case be a is not equal to b, I actually know that a plus b is 3, regardless of which a and which b is. Anyway, this all goes to show you, any true statement has lots and lots of proofs. The first step is just getting a proof, but then you can make the second step trying to find an easier proof, or an easier to read proof, or a shorter proof, a more natural proof, a more instructive proof. There are many different dimensions on which you could judge proofs, and so it's often helpful to have different methods of proving the same things. Let's do one last example here of cases. Let's prove that if I start with an odd integer, and I square it and add 7, then I always get a multiple of 8. Now, it's pretty tempting for this proof to start with so then x squared plus 7 works out to be 2k plus 1 squared plus 7, which is 4k squared plus 4k plus 8. Now, the 8, of course, is a multiple of 8, so that's good. But if you think through all the questions we've done of this sort over the course of the semester, you're kind of expecting an 8 to pop up out here, but it didn't. Instead, I got 2 4s. And I can't really get immediately to an 8. And so here, actually, I have to realize that what I need to do in order to finish this question is break into cases. And again, this is what I called the last lecture, making your own cases. No part of this question suggests that you should use cases. And yet, cases are almost necessary in order to write a proof of this. What cases am I going to use? Well, I'm actually going to break into cases based on whether k itself is even or odd. What does it look like if k is even? You churn through some algebra. And look at that. That's what we were looking for. A big algebra expression that I can factor an 8 out of. And great, that goes ahead and gets us that case. If instead k is odd, then there exists L and Z, such that k is 2L plus 1. And so what does that mean? That means that x squared plus 7, if I write it out from before, is now going to be 4 times 2L plus 1 squared, plus 4 times 2L plus 1, plus 8. I've got more algebra to churn through this time. So this is going to be 16L squared plus 16L plus 4 plus 8L plus 4 plus 8, which is going to be 16L squared plus 24L plus 16. And lo and behold, I can factor an 8 out of that. And so, if I take m to be that thing, then x squared plus 7 is 8 times m, and so x squared plus 7 is a multiple of 8. Alright, that completes that case, and since all integers are even or odd, that means we are done with our proof. Hopefully that gives you enough to work with to get started talking about proof by cases. In the next video, I'm going to start talking about our next proof method, which is going to be proof by induction. But stay tuned. I'll see you next time.